Imagine a place where time stands still, where gravity is so strong that not even light can escape. This isn't science fiction, it's the reality of black holes, one of the most fascinating and mysterious phenomena in our universe. For centuries, the idea of such cosmic entities was mere speculation, but today, we have concrete evidence of their existence. Join us as we embark on a journey through time, exploring the complete history of black hole discovery, from the early theoretical musings of brilliant minds to the groundbreaking observations that confirmed their existence. This is a story of curiosity, perseverance, and the relentless pursuit of understanding the cosmos. So, buckle up, because we're about to dive into the incredible tale of how we uncovered the secrets of black holes. Ancient precursor ideas. Long before the term black hole was coined, ancient civilizations pondered the nature of the cosmos and the existence of celestial bodies that defied conventional understanding. In the Indian Vedic texts, for instance, there are references to dark celestial entities that could swallow light. These texts, dating back thousands of years, describe dark stars that exert a powerful gravitational pull, a concept eerily reminiscent of modern black hole theories. Similarly, in ancient Chinese astronomy, there were mentions of heavenly voids that could consume stars, suggesting an early intuition about the existence of such phenomena. The ancient Greeks also contributed to the precursor ideas of black holes. Philosophers like Anaxagoras and Democritus speculated about the infinite divisibility of matter and the existence of voids in space. Their ideas, though not directly about black holes, laid the groundwork for understanding the nature of space and the possibility of regions where matter could be infinitely compressed. These philosophical musings were not based on empirical evidence, but rather on logical deductions and abstract reasoning, which were revolutionary for their time. In the Islamic Golden Age, scholars like Alhazen made significant strides in optics and the nature of light. His work on the behavior of light and its interaction with matter indirectly influenced later theories about how black holes could bend and trap light. The concept of a dark star that could emit no light was not explicitly stated, but the foundational work in optics and astronomy during this period set the stage for future explorations. These ancient ideas, though primitive by today's standards, demonstrate a persistent human curiosity about the mysteries of the universe. The dark star hypothesis. During the late 18th century, a curious idea began to take shape in the minds of astronomers and physicists. This concept, later known as the dark star hypothesis, emerged from the work of John Michell, an English clergyman and natural philosopher. Michell pondered the existence of objects so massive and dense that their gravitational pull would prevent light from escaping. He proposed that such dark stars could exist, though the technology of the time was far from capable of detecting them. This was a radical idea, challenging the understanding of stars and gravity. Michell's work laid the groundwork for what would eventually become the modern concept of black holes. The dark star hypothesis gained traction in the scientific community, particularly through the contributions of Pierre-Simon Laplace, a French mathematician and astronomer. Laplace independently proposed a similar idea, suggesting that invisible, massive objects could exist in space, exerting gravitational forces but emitting no light. His calculations, like Michell's, were based on Newtonian mechanics. However, both scientists faced skepticism, as their ideas were purely theoretical and lacked empirical evidence. The hypothesis remained largely speculative, a fascinating thought experiment rather than a widely accepted astronomical phenomenon. In the 19th and early 20th centuries, the dark star hypothesis faded into the background as other astronomical discoveries took center stage. The concept of black holes was not entirely forgotten, but it was overshadowed by more pressing scientific inquiries. It wasn't until the advent of Einstein's theory of general relativity that the idea of dark stars resurfaced with renewed vigor. Einstein's equations described the warping of space-time by massive objects, paving the way for a more rigorous understanding of what we now call black holes. The dark star hypothesis, though primitive by modern standards, was a crucial stepping stone in the journey towards this understanding. John Michell's contribution. In the late 18th century, a country parson named John Michell, who was also a Fellow of the Royal Society, proposed an idea that would later be recognized as a significant step towards the concept of black holes. Michell was a man of diverse interests, ranging from geology to astronomy, and his intellectual curiosity led him to ponder the nature of stars and their properties. He was particularly intrigued by the idea that some stars might be so massive and dense that their gravitational pull could prevent light from escaping. This notion was groundbreaking for its time, as it predated the development of general relativity by over a century. Michell's work was inspired by Newton's theory of gravity, which he used to calculate the conditions under which a star's escape velocity would exceed the speed of light. Although the speed of light was not precisely known at the time, Michell's reasoning was fundamentally sound. He suggested that such objects, which he called dark stars, would be invisible to the naked eye but could be detected through their gravitational effects on nearby visible objects. This idea laid the groundwork for future explorations into the nature of black holes, even though the term black hole would not be coined until much later. Michell's contributions were not immediately recognized or widely accepted. The scientific community of his time was still grappling with the implications of Newton's theories, and the concept of dark stars was considered somewhat speculative. However, Michell's ideas were not entirely forgotten. They were revisited and expanded upon by later scientists, particularly as the understanding of light and gravity evolved. One of the key milestones in the history of black hole discovery was the development of Einstein's theory of general relativity in 1915. This theory provided a more comprehensive framework for understanding gravity and its effects on the fabric of spacetime. It was not until 1939 that the term black hole was first used by the physicist J. Robert Oppenheimer, who described the phenomenon in a paper discussing the collapse of massive stars. This marked a significant shift in the scientific community's understanding of black holes, as it provided a more precise and mathematically rigorous description of their properties. The practical implications of Michell's ideas became more apparent as observational evidence for black holes began to accumulate. In the mid-20th century, astronomers started to detect unusual phenomena in the universe that could not be explained by conventional astrophysical models. For example, the discovery of quasars and other highly energetic objects in the 1960s suggested the presence of extremely massive and compact objects at their centers. These observations were consistent with the idea of black holes, as they required a source of gravity that could account for the immense energy output. The first strong candidate for a black hole was identified in the 1970s with the discovery of Cygnus X, a binary star system in which one of the components was inferred to be a black hole based on its 10th ray emissions and the dynamics of the system. This discovery provided compelling evidence for the existence of black holes and validated many of the theoretical predictions that had been made over the centuries. Michell's early insights, though initially overlooked, were thus vindicated by the advancements in observational astronomy and theoretical physics. Pierre-Simon Laplace's work. During the late 18th century, a French mathematician and astronomer named Pierre-Simon Laplace made significant contributions to the early understanding of what would later be known as black holes. His work was part of a broader effort to comprehend the nature of gravity and its effects on celestial bodies. Laplace was intrigued by the concept of gravitational forces and their implications. He pondered what would happen if an object became so dense that its gravitational pull was immense. This line of thinking led him to propose the existence of what he called dark stars. These dark stars, as Laplace envisioned them, were objects so massive and dense that their gravitational pull prevented any light from escaping. This idea was groundbreaking for its time, as it predated the formal concept of black holes by over a century. Laplace's work was speculative, rooted in the Newtonian understanding of gravity. He suggested that if a star's radius became smaller than a certain critical value, its escape velocity would exceed the speed of light, making it invisible. This critical radius is now known as the Schwarzschild radius, named after the physicist who later formalized it. Laplace's ideas were not widely accepted during his time. The scientific community of the late 18th and early 19th centuries was not yet ready to embrace such radical concepts. Additionally, the technology to observe or verify the existence of such objects was non-existent. Laplace himself later withdrew his own ideas, possibly due to the lack of empirical evidence and the skepticism of his peers. Despite this, his work laid the foundation for future explorations into the nature of black holes. The significance of Laplace's contributions became apparent much later, as the field of astrophysics advanced. His theoretical framework provided a starting point for scientists to build upon. When Albert Einstein developed his theory of general relativity in the early 20th century, it offered a more robust mathematical foundation for understanding the phenomena Laplace had speculated about. Einstein's equations predicted the existence of objects with such strong gravitational fields that light could not escape, aligning with Laplace's earlier ideas. This connection highlighted the foresight of Laplace's work and its enduring relevance in the study of black holes. Einstein's theory of relativity. In the early 20th century, Albert Einstein revolutionized our understanding of gravity and the universe with his theory of relativity. This groundbreaking work introduced the idea that massive objects, like stars and planets, warp the fabric of space-time around them, much like a heavy ball placed on a stretched rubber sheet. This warping of space-time is what we perceive as gravity. Einstein's equations predicted that if an object were massive enough, it could create a warp so deep that nothing, not even light, could escape from it. These objects, later dubbed black holes, were initially considered a mathematical curiosity rather than real astronomical entities. Einstein's theory also introduced the concept of event horizons, the point of no return around a black hole. Beyond this boundary, the warping of space-time is so extreme that all paths lead inward. This idea was purely theoretical at first, as black holes were not observed directly. However, Einstein's work laid the foundation for future discoveries. His equations also predicted that black holes could merge, releasing enormous amounts of energy in the form of gravitational waves. These ripples in space-time were finally detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, providing strong indirect evidence for the existence of black holes. The theory of relativity also suggested that black holes could come in different sizes. Stellar black holes, formed from the remnants of massive stars, are relatively small, with masses ranging from a few to tens of times that of our sun's supermassive black holes. On the other hand, reside at the centers of galaxies and have masses millions or even billions of times that of the sun. The Milky Way galaxy, for instance, has a supermassive black hole at its core, known as Sagittarius A star. The discovery of these objects has been a testament to the predictive power of Einstein's theory. Moreover, Einstein's work hinted at the bizarre phenomena that occur near black holes. Time dilation, for example, means that time passes slower in stronger gravitational fields. This effect has been observed in various experiments, including the famous Haffel-Keating experiment, where atomic clocks on airplanes ticked slower than those on the ground. Another peculiar prediction was the existence of singularities, points of infinite density at the center of black holes. These singularities challenge our understanding of physics, as they suggest that Einstein's theory breaks down at these extreme conditions. This has led to ongoing research in quantum gravity, aiming to reconcile general relativity with quantum mechanics. Schwarzschild solution. In the early 20th century, the understanding of gravity took a dramatic turn with the advent of Albert Einstein's theory of general relativity. This groundbreaking framework described gravity not as a force, but as the curvature of space-time caused by mass and energy. It was within this revolutionary context that Carl Schwarzschild made his significant contribution. A German physicist and astronomer, Schwarzschild served in the army during World War I. Despite the challenging circumstances, he found time to delve into the complexities of Einstein's new theory. His work led to the development of a solution to the Einstein field equations that described the gravitational field of a point mass, a non-rotating, spherically symmetric object. This solution, now known as the Schwarzschild solution, was a significant milestone in the theoretical understanding of black holes, although the term black hole wouldn't be coined until much later. The Schwarzschild solution introduced a critical concept: the existence of a radius around a massive object within which nothing, not even light, could escape. This radius is now known as the Schwarzschild radius. It marked the boundary of a black hole, a region of space-time from which gravity's pull is so strong that escape is impossible. Schwarzschild's work was remarkable not only for its mathematical elegance, but also for its profound implications. It provided a concrete, if theoretical, basis for the existence of black holes, objects that had been speculated about, but not yet understood in the context of modern physics. His solution also laid the groundwork for future explorations into the nature of black holes, including the study of their event horizons and singularities. Schwarzschild's solution was a significant step forward, but it was just the beginning. The concept of black holes remained largely theoretical for decades. It wasn't until the latter half of the 20th century that astronomers began to gather observational evidence supporting their existence. The Schwarzschild solution, however, remained a cornerstone of black hole physics. It provided a simple yet powerful model that could be built upon and expanded. For instance, it was later generalized to include rotating black holes, leading to the Kerr solution, which is more realistic for astrophysical black holes. The Schwarzschild solution also played a crucial role in the development of the theory of Hawking radiation, which suggests that black holes can emit particles and eventually evaporate. This theoretical framework has been instrumental in shaping our understanding of some of the most enigmatic and fascinating objects in the universe. The birth of modern astrophysics. The study of black holes has its roots in the birth of modern astrophysics, a period marked by a shift from mere observation to a deeper understanding of the universe's underlying physical principles. This transformation was driven by the advent of new technologies and theoretical breakthroughs. The telescope, for instance, allowed astronomers to observe celestial phenomena with unprecedented clarity. Meanwhile, the development of classical mechanics and later, quantum mechanics, provided the mathematical tools necessary to interpret these observations. These advancements set the stage for the theoretical exploration of black holes, even before their existence was confirmed. One of the earliest milestones in this journey was the formulation of Newton's law of universal gravitation. This law described how masses attract each other, laying the groundwork for understanding the gravitational forces at play in the cosmos. However, it was not until the 19th century that the concept of a body so massive that not even light could escape its gravitational pull began to take shape. This idea was first proposed by John Michell and later independently by Pierre-Simon Laplace. They imagined a dark star with a gravitational pull so strong that light, then thought to be particles, would be unable to escape. This was a radical concept, as it challenged the prevailing notion that light was unaffected by gravity. The birth of modern astrophysics also saw the development of the theory of general relativity by Albert Einstein. This theory revolutionized our understanding of gravity, describing it not as a force, but as the curvature of space-time caused by mass and energy. Einstein's equations predicted the existence of black holes, although he himself was initially skeptical about their physical reality. The term black hole was coined much later, in 1967, by the physicist John Wheeler. Meanwhile, the first observational evidence for black holes came from the study of binary star systems. In these systems, a visible star orbits an invisible companion, which is inferred to be a black hole due to its gravitational effects and the emission of tinth rays, thought to be from accreting matter. This evidence, along with subsequent discoveries, solidified the place of black holes in astrophysics, transforming them from theoretical curiosities to accepted astronomical phenomena. Arthur Eddington's reluctance. In the early 20th century, the concept of black holes emerged from the equations of general relativity, formulated by Albert Einstein. These mathematical solutions described regions of space where the gravitational pull was so strong that nothing, not even light, could escape. However, the idea was met with skepticism, not just because it challenged conventional understanding of physics, but also because it seemed to defy common sense. One of the most prominent figures who initially resisted the notion of black holes was the British astrophysicist Arthur Eddington. Eddington was a towering figure in the scientific community, renowned for his work in astrophysics and his popularization of Einstein's theory of relativity. He was also deeply committed to the idea that the physical world should make sense in human terms. The concept of a black hole, with its infinite density and ability to trap light, seemed to violate this principle. Eddington famously quipped, "First think there should be a law of nature to prevent a star from behaving in this absurd way." This reluctance was not merely a personal quirk, but reflected a broader scientific skepticism about the implications of general relativity. Despite his initial resistance, Eddington played a crucial role in advancing the understanding of black holes. He was one of the first scientists to recognize the significance of the Schwarzschild solution, a set of equations that described the gravitational field around a non-rotating black hole. Eddington's work helped to lay the groundwork for future research, even if he himself was not entirely convinced of their physical reality. His reluctance, in a way, underscored the revolutionary nature of the idea. It took decades for the scientific community to fully accept the existence of black holes, and even longer for observational evidence to catch up with theory. The turning point came with the discovery of quasars and other high-energy astronomical phenomena in the 1960s. These objects exhibited properties that could only be explained by the presence of extremely massive and compact objects, such as black holes. Eddington's reluctance, once a symbol of scientific caution, became a testament to the slow but steady progress of scientific understanding. Today, black holes are not just accepted as real, but are a central part of astrophysics, from the study of galaxy formation to the exploration of quantum gravity. Eddington's initial skepticism serves as a reminder of how even the most brilliant minds can struggle with ideas that challenge the boundaries of human comprehension. Subramanian Chandrasekhar's limit. In the vast expanse of astrophysics, few concepts are as pivotal as the Chandrasekhar limit. This theoretical threshold, named after the Indian-American astrophysicist Subramanian Chandrasekhar, marks the maximum mass a stable white dwarf star can have. Beyond this limit, the star's core cannot support its own weight, leading to a supernova explosion or the formation of a neutron star. Chandrasekhar's work, conducted in the 1930s, was groundbreaking, challenging the prevailing theories of the time and laying the foundation for modern astrophysics. Chandrasekhar's limit is approximately 1.4 times the mass of the Sun. This means that if a white dwarf star, the remnant of a star like our Sun, has a mass greater than this limit, it will undergo a catastrophic collapse. The limit is derived from the balance between the star's gravitational force, which pulls inward, and the electron degeneracy pressure, a quantum mechanical effect that resists compression. When the star's mass exceeds the Chandrasekhar limit, the electron degeneracy pressure can no longer withstand the gravitational force, leading to the star's collapse. This collapse can result in a Type I supernova, one of the most energetic events in the universe, or the formation of a neutron star, an incredibly dense object composed primarily of neutrons. The significance of the Chandrasekhar limit extends beyond theoretical astrophysics. It plays a crucial role in our understanding of stellar evolution and the life cycles of stars. For instance, it helps explain why some stars end their lives in spectacular supernova explosions while others quietly fade away as white dwarfs. Moreover, the Chandrasekhar limit is a key factor in the study of dark energy and the accelerating expansion of the universe. Type I supernovae, which occur when a white dwarf exceeds the Chandrasekhar limit, serve as standard candles for measuring cosmic distances. By observing these supernovae, astronomers can map the universe's expansion and probe the mysterious force driving it. Chandrasekhar's work on the limit was initially met with skepticism, particularly from prominent figures like Arthur Eddington. However, subsequent observations and theoretical advancements have firmly established the Chandrasekhar limit as a cornerstone of astrophysics. Today, it is a testament to the power of theoretical physics and the enduring legacy of Subramanian Chandrasekhar, who was awarded the Nobel Prize in Physics in 1983 for his contributions to the structure and evolution of stars. His limit continues to inspire and guide researchers in their quest to unravel the mysteries of the universe. J. Robert Oppenheimer's predictions. In the vast expanse of astrophysical theories, J. Robert Oppenheimer stands out as a visionary who significantly contributed to the understanding of black holes. His work, particularly in the 1930s, laid the groundwork for much of what we now accept about these enigmatic cosmic entities. Oppenheimer, along with his student Hartland Snyder, proposed a radical idea that massive stars could collapse under their own gravity to form singularities, regions of infinite density from which not even light could escape. This concept, now a cornerstone of black hole theory, was initially met with skepticism. The scientific community struggled to reconcile the implications of such objects with the known laws of physics. Oppenheimer's predictions were rooted in the principles of general relativity, Einstein's revolutionary theory of gravity. He and Snyder used these principles to describe the final stages of stellar evolution, suggesting that stars several times more massive than the Sun could end their lives in a catastrophic collapse. Their calculations indicated that once the collapse began, it would be inevitable and unstoppable, leading to the formation of a singularity. This idea was groundbreaking, as it challenged the prevailing notion that stars simply burned out and faded away. Oppenheimer's work also introduced the concept of the event horizon, the boundary around a black hole beyond which nothing can escape. The theoretical framework established by Oppenheimer and Snyder was ahead of its time. It took decades for technological advancements to catch up and provide observational evidence supporting their predictions. In the 1960s and 1970s, the discovery of quasars and other high-energy astronomical phenomena hinted at the existence of black holes. These objects exhibited properties that aligned with Oppenheimer's theories, such as immense gravitational pull and the emission of intense radiation. The confirmation of black holes as real, physical entities validated Oppenheimer's early work and cemented his legacy in the field of astrophysics. Oppenheimer's contributions extended beyond the initial predictions. He also explored the concept of black hole entropy and the thermodynamic properties of these objects. His insights paved the way for future researchers to delve deeper into the nature of black holes and their role in the universe. Today, black holes are a central topic in astrophysics, and Oppenheimer's predictions remain a fundamental part of our understanding. His work serves as a testament to the power of theoretical physics and the importance of pushing the boundaries of human knowledge. The term black hole is coined. The term black hole was first coined by the American physicist John Wheeler in 1967. This was a pivotal moment in the history of astrophysics, as it provided a concise and evocative name for a phenomenon that had been theorized for over 2 centuries. Wheeler's choice of words captured the essence of these mysterious objects, which were thought to be regions of space where gravity was so intense that nothing, not even light, could escape. The term quickly gained popularity and became the standard way to refer to these enigmatic cosmic entities. Before Wheeler's coinage, the concept of black holes was discussed using various other terms. Early theorists, like Jean-Michel and Pierre-Simon Laplace, referred to them as dark stars. These terms, however, did not convey the same sense of finality and mystery as black hole. Wheeler's terminology was a stroke of genius, as it immediately resonated with the scientific community and the public. It also helped to shift the perception of black holes from being mere mathematical curiosities to being real, physical objects worthy of serious study. The coinage of the term black hole also coincided with a surge in theoretical and observational work on these objects. In the late 1960s and early 1970s, physicists like Roger Penrose and Stephen Hawking made significant contributions to the understanding of black hole physics. Meanwhile, astronomers were beginning to gather observational evidence for the existence of black holes. The term black hole became a rallying point for this research, fostering a sense of excitement and urgency in the scientific community. It also helped to popularize the study of black holes, inspiring a new generation of physicists and astronomers to explore these fascinating objects. First candidates for black holes. The journey to identify the first candidates for black holes began with a deep understanding of their theoretical underpinnings. Long before any observational evidence existed, scientists like Jean-Michel and Pierre-Simon Laplace speculated about the existence of objects so massive that not even light could escape their gravitational pull. These early ideas laid the groundwork for what would later be known as black holes. The concept was purely theoretical, rooted in Newtonian physics, and it wasn't until the advent of Einstein's theory of general relativity that the modern understanding of black holes began to take shape. This theory provided a more accurate description of gravity and its effects on spacetime, making the idea of black holes more plausible. As the 20th century progressed, astronomers started to look for objects that fit the theoretical descriptions of black holes. One of the first candidates identified was Cygnus X, a strong 10th-ray source in the constellation Cygnus. This object was found to be a binary system, where one component was a massive, invisible object pulling material from its companion star. The behavior of this system closely matched the predictions for a black hole, making it a prime candidate. The 10th ray emissions were thought to be generated by the accretion disk of hot gas swirling around the black hole, a process that releases enormous amounts of energy. This discovery was a significant milestone, as it provided the first strong observational evidence for the existence of black holes. Another early candidate was the quasar 3C273, one of the first quasars ever identified. Quasars are extremely luminous active galactic nuclei, and their energy output is thought to be powered by supermassive black holes at their centers. The immense energy and the jets of material ejected at nearly the speed of light were consistent with the behavior expected from a black hole. These observations, along with others, helped to solidify the idea that black holes were not just theoretical constructs, but real astronomical objects. The study of these candidates has since led to a deeper understanding of black holes and their role in the universe, from their formation and evolution to their impact on the surrounding environment. Cygnus X, the first strong candidate. In the vast expanse of the cosmos, Cygnus X emerged as a beacon of discovery, challenging and reshaping our understanding of black holes. This celestial object, located in the constellation Cygnus, became the first strong candidate for a black hole, sparking a revolution in astrophysics. The journey to this realization was a tapestry of theoretical leaps and observational breakthroughs, woven together by the relentless pursuit of scientific inquiry. The story began with the theoretical groundwork laid by Albert Einstein's general theory of relativity, which predicted the existence of objects with gravitational fields so intense that not even light could escape. These were the seeds of the black hole concept. However, it wasn't until the mid-20th century that scientists started to seriously consider the possibility of black holes in the universe. The theoretical work of physicists like Carl Schwarzschild, Roy Kerr, and Subramanian Chandrasekhar provided the mathematical frameworks that described the properties and behaviors of these enigmatic objects. Observational astronomy took a significant leap forward with the advent of space-based telescopes and advanced detection technologies. Cygnus X was first identified as a strong 10th ray source in the early 1960s. It was one of the first objects studied by the Uhuru satellite, the first 10th ray astronomy satellite launched by NASA in 1970. The intense 10th ray emissions from Cygnus X suggested the presence of a compact, massive object. Astronomers observed a blue supergiant star, HD 226868, orbiting an invisible companion. The behavior of this star, including its orbital characteristics and the nature of the 10th ray emissions, pointed towards the companion being a black hole. The breakthrough came with the measurement of the mass of the invisible companion. Using Doppler shift measurements and other observational techniques, astronomers determined that the companion had a mass at least 8-10 times that of the Sun. This was well above the theoretical limit for a neutron star, the most massive known type of star that isn't a black hole. The only remaining explanation was a black hole. The discovery of Cygnus X provided the first strong evidence for the existence of black holes, validating decades of theoretical work and opening new avenues for exploration in astrophysics. Quasars and active galactic nuclei. Quasars and active galactic nuclei, AGN, represent some of the most energetic and enigmatic phenomena in the universe. These cosmic powerhouses are believed to be driven by supermassive black holes at the centers of galaxies. The study of quasars and AGN has significantly advanced our understanding of black hole physics and galaxy evolution. Quasars, short for quasi-stellar radio sources, were first identified in the 1960s. They appeared as point-like sources of radio waves, similar to stars, but with spectra that indicated they were far more distant and energetic. This paradox suggested that quasars were incredibly luminous objects, emitting vast amounts of energy from relatively small regions. The discovery of quasars challenged existing astronomical theories and sparked intense debate about their nature. Active galactic nuclei are the regions at the centers of galaxies that exhibit high levels of activity, often outshining the entire galaxy. These nuclei can emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. The energy output is so immense that it can exceed the combined luminosity of all the stars in the galaxy. AGN are classified into several types, including Seyfert galaxies, radio galaxies, and blazars, each with distinct observational characteristics. The unifying model for AGN is that they are powered by accretion disks of hot gas and dust swirling around supermassive black holes. As material falls into the black hole, it releases gravitational energy, heating the surrounding gas and producing the observed radiation. The connection between quasars and AGN became clear as astronomical observations improved. Quasars are now understood to be a specific type of AGN, viewed from a particular angle where the jet of relativistic particles emitted by the black hole points directly towards the observer. This alignment enhances the observed brightness and makes quasars appear as distant, point-like sources. The study of quasars and AGN has provided crucial insights into the growth and evolution of supermassive black holes. These objects play a pivotal role in shaping the galaxies they inhabit, influencing star formation and galactic structure through their immense energy output. The ongoing research into quasars and AGN continues to push the boundaries of astrophysics, offering a window into the most extreme environments in the universe. Pulsars and neutron stars. In the vast expanse of the cosmos, pulsars and neutron stars have captivated astronomers and astrophysicists for decades. These celestial objects, born from the remnants of massive stars that have exploded in supernovae, are among the most exotic and intriguing phenomena in the universe. Pulsars, in particular, are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation. Their discovery has been pivotal in our understanding of black holes and the extreme physics that governs their behavior. The journey began with the theoretical groundwork laid by scientists exploring the life cycles of stars. It was understood that when a massive star exhausts its nuclear fuel, it undergoes a catastrophic collapse, leading to a supernova explosion. The core of the star, depending on its mass, could either form a neutron star or a black hole. Neutron stars, as the name suggests, are composed almost entirely of neutrons, packed so densely that a teaspoon of neutron star material would weigh billions of tons on Earth. Pulsars are a subset of neutron stars that emit regular pulses of radiation, akin to a cosmic lighthouse. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish, though the term pulsar was coined later. This discovery was initially met with skepticism, as the regularity of the pulses led some to speculate about extraterrestrial origins. However, further observations and theoretical work confirmed that pulsars were indeed natural phenomena. The pulses are caused by the rotation of the neutron star, with beams of radiation sweeping through space like a lighthouse beam. The regularity of these pulses makes pulsars incredibly useful as natural clocks, allowing scientists to study a variety of astrophysical phenomena, including the properties of gravity and the interstellar medium. Pulsars and neutron stars have also played a crucial role in the study of black holes. Observations of binary systems, where a neutron star orbits a black hole, have provided valuable insights into the dynamics of these extreme environments. The gravitational interactions in such systems can lead to the emission of gravitational waves, ripples in the fabric of space-time predicted by Einstein's theory of general relativity. The detection of these waves, first achieved in 2015 by the LIGO collaboration, has opened a new window into the universe, allowing scientists to probe the nature of black holes and the fundamental laws of physics. The discovery of Sagittarius A*. In the vast expanse of our galaxy, the Milky Way, lies a mysterious and enigmatic object known as Sagittarius A star. This supermassive black hole, residing at the galactic center, has been a subject of intense study and fascination for astronomers. The journey to its discovery began with the observation of peculiar radio emissions from the constellation Sagittarius. These emissions, first detected in the 1950s, were unlike anything seen before, piquing the curiosity of scientists. Over the decades, advancements in radio astronomy and observational techniques allowed researchers to pinpoint the source of these emissions more accurately. By the 1970s, it became clear that the emissions were originating from a region near the galactic center, later identified as Sagittarius A star. The nature of Sagittarius A * remained a mystery until the late 20th century. Astronomers observed stars orbiting an invisible, massive object at incredibly high speeds. This behavior could only be explained by the presence of a supermassive black hole. The orbits of these stars, particularly the star S2, provided crucial evidence. S2's orbit around Sagittarius A * takes about 16 years, and its closest approach brings it within a mere 17 light hours of the black hole. These observations match the predictions of Einstein's theory of general relativity, confirming the existence of a black hole at the galactic center. The data also allowed scientists to estimate the mass of Sagittarius A *, which is approximately 4 million times that of our Sun. The discovery of Sagittarius A * has opened up new avenues for understanding black holes and the dynamics of galaxies. It has provided a unique laboratory for testing theories of gravity and the behavior of matter in extreme environments. Recent advancements, such as the Event Horizon Telescope's image of the shadow of a black hole in M87, have further fueled excitement and anticipation. While Sagittarius A * itself has not been directly imaged yet, the ongoing efforts to capture its shadow promise to reveal even more about these cosmic giants. The study of Sagittarius A * continues to be a cornerstone of modern astrophysics, offering insights into the fundamental nature of the universe. LIGO and gravitational waves. The study of black holes has been a fascinating journey, filled with theoretical leaps and groundbreaking discoveries. One of the most significant chapters in this story involves the Laser Interferometer Gravitational Wave Observatory, LIGO, and the detection of gravitational waves. These ripples in space-time, predicted by Albert Einstein's general theory of relativity, have opened a new window into the cosmos, allowing scientists to observe some of the most violent and energetic processes in the universe. LIGO's journey began with a vision to detect these elusive gravitational waves. The observatory consists of two massive detectors, one in Livingston, Louisiana, and the other in Hanford, Washington. Each detector is an L-shaped interferometer with arms 4 kilometers long. Laser beams are split and sent down these arms, bouncing off mirrors at the end. When a gravitational wave passes through, it subtly changes the distance between the mirrors, creating a tiny but detectable shift in the laser light. This shift is what scientists look for, a faint whisper from the cosmos. The first detection of gravitational waves by LIGO was a monumental moment. On September 14, 2015, both detectors picked up a signal from the merger of two black holes about 1.3 billion light-years away. This event, dubbed GW150914, marked the first direct observation of gravitational waves and the first direct detection of black holes. The signal matched the predictions of general relativity, confirming a major aspect of Einstein's theory. Since then, LIGO and its international partners have detected numerous other gravitational wave events, including mergers of neutron stars and other black hole collisions. Gravitational waves carry information about their origins that cannot be obtained through traditional astronomical observations. They provide a unique way to study black holes, neutron stars, and other exotic objects. For instance, the detection of GW170817, a merger of two neutron stars, was accompanied by observations in gamma rays, T rays, and visible light. This multi-messenger astronomy approach has given scientists unprecedented insights into the physics of these extreme events. LIGO's discoveries have not only deepened our understanding of black holes, but also opened up new avenues for exploring the universe. The Event Horizon Telescope. Black holes, once merely the stuff of science fiction, have become a cornerstone of modern astrophysics. The journey to their discovery and understanding is a tale of human curiosity and technological ingenuity. Early theories about these cosmic enigmas began with Carl Schwarzschild's solution to Einstein's field equations in 1916, which described a region of space from which nothing, not even light, could escape. This theoretical foundation laid the groundwork for future explorations. However, it wasn't until the mid-20th century that astronomers started to gather observational evidence supporting the existence of black holes. The discovery of quasars and 10th-ray sources in the 1960s provided tantalizing clues, but direct evidence remained elusive. The Event Horizon Telescope, EHT, represents a monumental leap in our quest to observe black holes directly. This isn't a single telescope, but a global network of radio observatories that work in unison to capture images of black holes. By combining data from multiple sites, the EHT achieves an angular resolution equivalent to a telescope the size of the Earth. This unprecedented capability allows scientists to peer into the heart of our galaxy and beyond. The EHT's most famous achievement came in 2019 when it unveiled the first-ever image of a black hole, specifically the supermassive black hole at the center of the galaxy, M87. This groundbreaking image provided visual confirmation of the theoretical predictions made over a century ago. The EHT's work doesn't stop at capturing images. It also aims to study the immediate environment around black holes, known as the event horizon. This region is where the gravitational pull becomes so strong that not even light can escape. By observing the event horizon, scientists hope to test the fundamental theories of general relativity and quantum mechanics. The EHT's data has already provided insights into the dynamics of accretion disks, the swirling masses of gas and dust that spiral into black holes. These observations help astronomers understand the processes that power quasars and other high-energy phenomena in the universe. The EHT's success is a testament to international collaboration and technological innovation. The project involves researchers and observatories from around the world, including the United States, Europe, Japan, and Chile. Each site contributes unique data that, when combined, creates a comprehensive picture of black holes. The EHT's achievements have not only advanced our understanding of these mysterious objects, but also inspired a new generation of astronomers and physicists. As technology continues to evolve, the EHT and similar projects will undoubtedly uncover even more secrets about the fabric of the universe. The first image of a black hole. The concept of a black hole has fascinated scientists and the public alike for decades. The journey to capture the first image of a black hole was a monumental task that combined theoretical physics, advanced technology, and international collaboration. It all began with the understanding that black holes are regions in space where the gravitational pull is so strong that nothing, not even light, can escape. This idea was first proposed as a mathematical solution to the equations of general relativity, but it took centuries for technology to catch up with theory. The Event Horizon Telescope, EHT, project, a global network of radio observatories, was instrumental in capturing the first image of a black hole. By linking telescopes around the world, the EHT effectively created an Earth-sized virtual telescope. This allowed scientists to achieve the unprecedented resolution needed to observe the immediate surroundings of a black hole. The target of their efforts was the supermassive black hole at the center of the galaxy M87, known as M87 star. The image revealed a bright ring of light surrounding a dark central region, the shadow of the black hole itself. This groundbreaking achievement provided direct visual evidence of the existence of black holes, confirming decades of theoretical work. The image of M87* showed a ring of light bent by the intense gravity of the black hole, a phenomenon known as gravitational lensing. This effect is predicted by Einstein's theory of general relativity. The bright ring corresponds to the accretion disk, a swirling disk of hot gas and dust that orbits the black hole at nearly the speed of light. The dark central region, or shadow, is where the gravitational pull is so strong that light cannot escape. This image not only provided a visual confirmation of black holes, but also offered insights into their behavior and the nature of space-time itself. It marked a significant milestone in our understanding of the universe and the fundamental forces that govern it. The success of the EHT project has opened new avenues for research. Scientists can now study the dynamics of black holes in greater detail, observing how they interact with their surroundings and influence the evolution of galaxies. The first image of a black hole has also sparked public interest and inspired a new generation of scientists. It serves as a testament to human ingenuity and the power of international collaboration in pushing the boundaries of scientific discovery. The journey to capture this image is a remarkable story of perseverance, innovation, and the relentless pursuit of knowledge. Black hole merger observations. The concept of black holes has fascinated scientists and the public alike, but it's the observation of black hole mergers that has truly captivated the world. These cosmic events are incredibly powerful, releasing vast amounts of energy in the form of gravitational waves. The first direct detection of gravitational waves, announced in 2016, was a monumental moment in astrophysics. This discovery, known as GW150914, was made by the Laser Interferometer Gravitational Wave Observatory, LIGO. It confirmed a major prediction of Albert Einstein's general theory of relativity and marked the beginning of a new era in astronomy. The detection of GW150914 was a result of a merger of two black holes, each with masses about 30 times that of the Sun. The event occurred roughly 1.3 billion years ago, but the gravitational waves only reached Earth in September 2015. This observation provided the first direct evidence of black hole mergers. Since then, LIGO and its European counterpart, Virgo, have detected several more black hole mergers. Each detection offers valuable insights into the nature of black holes and the universe itself. One of the most significant aspects of these observations is the information they provide about the black holes involved. For instance, the masses and spins of the black holes can be inferred from the gravitational wave signals. This data helps scientists understand the formation and evolution of black holes. Moreover, the detection of black hole mergers has opened up a new way to study the universe. Unlike traditional astronomy, which relies on electromagnetic radiation like visible light, X rays, or radio waves, gravitational wave astronomy allows scientists to probe the cosmos in an entirely new way. The future of black hole merger observations looks promising. With the ongoing upgrades to LIGO and Virgo, and the planned launch of space-based detectors like LISA, Laser Interferometer Space Antenna, scientists expect to detect even more black hole mergers. These advancements will not only increase the number of detections, but also improve the sensitivity and accuracy of the observations. This, in turn, will provide deeper insights into the physics of black holes and the fundamental nature of the universe. The study of black hole mergers is a rapidly evolving field, and each new discovery brings us closer to unraveling the mysteries of these enigmatic cosmic objects. Hawking radiation and black hole thermodynamics. In the vast expanse of astrophysics, few topics are as intriguing and complex as black holes. These cosmic entities, with their immense gravitational pull, have captivated scientists and enthusiasts alike. Among the most groundbreaking developments in black hole research are the theories surrounding Hawking radiation and black hole thermodynamics. These concepts have not only deepened our understanding of black holes, but also challenged our perceptions of the universe's fundamental laws. The journey began with the realization that black holes aren't entirely black. In the 1970s, physicist Stephen Hawking proposed that black holes can emit radiation, a phenomenon now known as Hawking radiation. This theory emerged from a blend of quantum mechanics and general relativity. Hawking suggested that particle-antiparticle pairs near the event horizon of a black hole could result in one particle being pulled in while the other escapes, effectively causing the black hole to lose mass over time. This was a radical idea, as it implied that black holes could evaporate, given enough time. The implications were profound, suggesting that black holes aren't eternal but have a finite lifespan. Building on this, scientists explored the thermodynamic properties of black holes. Jacob Bekenstein had earlier proposed that black holes have entropy, a measure of disorder or randomness. This idea was controversial because it suggested that black holes could have thermodynamic properties similar to those of ordinary physical systems. Hawking's work on radiation further supported this notion. Together, their theories led to the formulation of black hole thermodynamics, which draws parallels between the laws of thermodynamics and the behavior of black holes. For instance, the second law of thermodynamics, which states that the total entropy of an isolated system can never decrease, finds an analogy in the behavior of black holes. This law ensures that the total entropy of a black hole plus any surrounding matter always increases, much like the entropy in a thermodynamic system. The practical implications of these theories are vast. Understanding Hawking radiation and black hole thermodynamics has provided insights into the nature of quantum gravity, the unification of quantum mechanics, and general relativity. It has also raised questions about information loss paradoxes, where information about the state of particles falling into a black hole seems to be lost, challenging the principles of quantum mechanics. Scientists continue to explore these ideas, hoping to uncover more about the fundamental workings of the universe. Observational evidence, though challenging to obtain, has started to support these theories. For example, the detection of gravitational waves and the imaging of black holes, like the one at the center of galaxy M87, have provided valuable data that aligns with theoretical predictions. As technology advances, our understanding of these enigmatic cosmic objects will undoubtedly deepen, shedding more light on the mysteries of the universe. Information paradox and quantum gravity. The study of black holes has always been a fascinating journey, filled with mind-bending concepts and groundbreaking discoveries. One of the most intriguing aspects is the information paradox and its connection to quantum gravity. At the heart of this puzzle lies the conflict between quantum mechanics and general relativity. Quantum mechanics dictates that information about a system must always be conserved, while general relativity suggests that information can be lost forever when it falls into a black hole. This contradiction has puzzled scientists for decades, leading to intense research and debate. The information paradox gained prominence in the 1970s when physicist Stephen Hawking proposed that black holes can emit radiation, now known as Hawking radiation. This radiation causes black holes to slowly evaporate over time. The problem arises when considering what happens to the information of the matter that formed the black hole. If the black hole evaporates completely, the information seems to be lost, violating the principles of quantum mechanics. This paradox has sparked numerous theories and hypotheses, each attempting to reconcile the seemingly irreconcilable. One of the most promising avenues for resolving the information paradox is through the study of quantum gravity. Quantum gravity aims to unify quantum mechanics and general relativity into a single framework. Various approaches, such as string theory and loop quantum gravity, have emerged, each offering unique insights into the nature of black holes and the information paradox. String theory, for instance, suggests that black holes might have a microscopic structure that could preserve information. Loop quantum gravity, on the other hand, proposes that space itself has a discrete structure that could prevent information loss. Recent advancements in observational astronomy have provided new tools to study black holes and test these theories. The detection of gravitational waves by LIGO and the first image of a black hole by the Event Horizon Telescope have offered unprecedented insights into these enigmatic objects. These observations have not only confirmed many theoretical predictions, but also opened new avenues for exploring the information paradox and quantum gravity. As our understanding of black holes continues to evolve, so too does our grasp of the fundamental laws governing the universe. Black holes in popular culture. Black holes have long captivated the public imagination, evolving from obscure scientific concepts to mainstream cultural phenomena. Early depictions often leaned into the mysterious and terrifying aspects of these cosmic entities. Science fiction writers and filmmakers initially portrayed black holes as cosmic vacuum cleaners, capable of swallowing entire starships and planets. This trope was popularized in films like The Black Hole, 1979, which depicted a black hole as a swirling, glowing maw of destruction. Such portrayals, while dramatic, were far from accurate, but served to ignite public interest and curiosity. As scientific understanding of black holes deepened, so too did their representation in popular culture. Television shows like Star Trek and Doctor Who began to incorporate more nuanced portrayals, often using black holes as plot devices for time travel or interstellar exploration. These shows balanced scientific intrigue with creative storytelling, making complex concepts accessible to a broader audience. Video games also jumped on the bandwagon, with titles like Mass Effect and Elite Dangerous featuring black holes as both hazards and wonders to be explored. This shift reflected a growing public awareness and acceptance of black holes as real, albeit enigmatic, astronomical objects. In recent years, black holes have become a staple in mainstream media, thanks in part to groundbreaking scientific discoveries and advancements in visualization technology. The release of the film Interstellar, 2014, marked a significant milestone as it featured a scientifically accurate depiction of a black hole, thanks to consultations with astrophysicist Kip Thorne. This collaboration between science and Hollywood brought black holes into the cultural spotlight, sparking conversations and debates among both scientists and the general public. Social media platforms also played a role, with memes and viral posts often featuring black holes as a symbol of the unknown and the infinite. Moreover, the Event Horizon Telescope's historic capture of the first-ever image of a black hole in 2019 further cemented their place in popular culture. This image, known as the shadow of the black hole, became an instant icon, appearing on everything from t-shirts to coffee mugs. It also inspired a wave of artistic interpretations, from digital art to music videos, showcasing the enduring fascination with these cosmic giants. Black holes have transcended their scientific origins to become a cultural touchstone, symbolizing both the mysteries of the universe and the boundless potential of human curiosity and imagination. Current research and future prospects. The study of black holes has evolved significantly since their theoretical inception. Today, researchers are delving deeper into the mysteries of these cosmic entities, driven by advanced technologies and innovative theories. One of the most exciting areas of current research is the study of black hole mergers. Gravitational wave detectors, like LIGO and Virgo, have observed several such events, providing invaluable data. These observations help scientists understand the dynamics of black hole collisions and the resulting gravitational waves. The data also offers insights into the nature of space-time itself, confirming predictions made by Einstein's general theory of relativity. Another fascinating avenue of research is the study of supermassive black holes at the centers of galaxies. The Event Horizon Telescope, EHT, made history in 2019 by capturing the first-ever image of a black hole, specifically the one at the center of the galaxy M87. This achievement was a monumental step forward, allowing scientists to observe the shadow of a black hole and the surrounding accretion disk. Ongoing research aims to improve the resolution of these images and study the behavior of matter near the event horizon. Scientists are also investigating the role of supermassive black holes in galaxy formation and evolution, exploring how these massive objects influence the cosmos around them. Looking ahead, the future of black hole research is brimming with potential. Upcoming missions and projects promise to revolutionize our understanding of these enigmatic objects. The Laser Interferometer Space Antenna, LISA, a planned space-based gravitational wave observatory, will detect low-frequency gravitational waves, providing a new window into the universe. This mission could reveal the mergers of supermassive black holes, offering insights into the early universe and the growth of cosmic structures. Additionally, advancements in quantum gravity theories aim to reconcile general relativity with quantum mechanics, potentially unlocking the secrets of singularities at the heart of black holes. Moreover, the study of black hole thermodynamics and the information paradox continues to captivate researchers. The idea that black holes might emit radiation, as proposed by Stephen Hawking, has sparked intense debate and exploration. Scientists are investigating the nature of this radiation and its implications for the conservation of information. This research could lead to a deeper understanding of the fundamental laws of physics and the fabric of the universe. As technology advances and theoretical frameworks evolve, the future of black hole research holds the promise of groundbreaking discoveries, pushing the boundaries of human knowledge and our place in the cosmos. The role of black holes in the universe. Black holes, once merely theoretical constructs, have become central to our understanding of the universe. Their role is multifaceted, influencing everything from the evolution of galaxies to the very fabric of space-time. Initially, black holes were thought to be rare and exotic objects. However, it is now understood that they are common, with supermassive black holes residing at the centers of most, if not all, galaxies. These cosmic giants play a crucial role in galactic evolution. They regulate star formation by heating and disrupting the surrounding gas, thus influencing the overall structure and life cycle of galaxies. Additionally, The intense gravitational fields of black holes warp space-time, creating environments where the laws of physics are pushed to their limits. This makes them natural laboratories for testing theories of gravity and quantum mechanics. The discovery of quasars in the mid-20th century provided some of the first observational evidence for supermassive black holes. Quasars are extremely luminous objects found at the centers of distant galaxies, powered by the accretion of matter into supermassive black holes. This process releases enormous amounts of energy, making quasars some of the brightest objects in the universe. The study of quasars has not only confirmed the existence of supermassive black holes, but has also shed light on the early universe. By observing quasars at great distances, astronomers can peer back in time, studying the conditions and processes that shaped the universe in its infancy. Furthermore, the detection of gravitational waves from merging black holes has opened a new window into the cosmos. These ripples in space-time provide direct evidence of black hole interactions and offer insights into their formation and evolution. Black holes also play a pivotal role in the study of dark matter and dark energy. The motion of stars and gas around black holes can reveal the presence of dark matter, which exerts a gravitational influence but does not emit light. By analyzing these motions, astronomers can map the distribution of dark matter and infer its properties. Additionally, the growth of supermassive black holes over cosmic time is linked to the expansion of the universe, driven by dark energy. Understanding this connection is key to unraveling the mysteries of dark energy and the ultimate fate of the universe. Moreover, black holes are not just passive objects. They actively shape their surroundings. Jets of high-energy particles emitted by black holes can extend thousands of light years, influencing star formation and galactic dynamics. These jets are powered by the accretion disks of black holes, where matter spirals inwards, releasing vast amounts of energy. Studying these jets provides valuable information about the physics of accretion and the behavior of matter in extreme gravitational fields. And there you have it, folks. From the early musings of Jean-Michel and Pierre-Simon Laplace to the groundbreaking observations of the Event Horizon Telescope, our understanding of black holes has come a long way. We've journeyed through the mind-bending theories of Einstein, the pioneering work of Schwarzschild, and the thrilling discoveries of Cygnus X and Sagittarius A star. We've seen how black holes, once mere figments of theoretical physics, have become some of the most fascinating and well-studied objects in the universe. So what's next? The future of black hole research is brighter than ever. Scientists are already working on unraveling the mysteries of black hole mergers, studying the role of black holes in galaxy formation, and even exploring the possibility of harnessing black holes for energy. Who knows what we'll discover next? If you've enjoyed this journey through the history of black hole discovery, stay tuned for our next video, where we'll dive even deeper into the cosmos. Maybe we'll explore the enigmatic world of dark matter, or perhaps we'll take a closer look at the life cycle of stars. Whatever it is, you can be sure it'll be another mind-bending adventure. Don't forget to like, share, and subscribe for more out-of-this-world content. And as always, keep looking up, because the universe is full of wonders waiting to be discovered. Until next time, keep exploring.